this. Good evening. My name is Ki-Hyun Jo, and I'm going to represent my LAB3 beam vibration, which was to investigate the experimental of the static and dynamic behavior of a cantilever beam. Excuse me, there is a technical issues. So the outline is the main objects, experimental setup, and the result of each experimental, such as static measurements, dynamic measurements with a different condition, vibration control, summary, conclusions, and the reference that I'm going to talk about the equation later. So the main objects of this lab was to measure the vibration response of a cantilever beam with the different acceptance conditions, such as free or adding different dampers or put more force by dropping something, and to measure the natural frequency of each case by using the time domain and FFT analysis. And also to measure the damping ratio by using the logarithmic decrement method. And the last one is compare each damping ratio and observe the damping effect. So the experimental setup is, as you can see in the top right of the picture, we set up the Wheatstone bridge circuit, which constructed with the 320 ohm resistors and connected with the PEP, which is the red one. Then they set the cantilever beam with one fix and the free at the tip, just like what you can see on the right bottom of this slide. So for static measures, we didn't put any like force, like just like this. So if we say this is a beam, we didn't do this. We just see how the cantilever beam behaves. So the main purpose of this measurement was to determine the sensitivity of the strain gauge at the static condition. And you can see on the graph on the right bottom, the slope of the graph represents the sensitivity of the gauge, which was 17,749.19 millimeter per volume. So you can see a linear relationship between tip displacement and voltage was observed. And to prove, make sure that the beam is working with Hooke's law, then we also measure with the beam equivalent stiffness. So the displacement was measured after applying static loads to the cantilever beam. A linear relationship between force and displacement was observed as well, as you can see on the graph. And the slope also represents the stiffness of the beam, which is 0.0252 Newton divided by millimeter. And the linear behavior also proves that the cantilever beam works with the Hooke's law. So then we're gonna move to dynamic measurements, the initial displacement excitation. So this, to explain this, so if we say this is beam and this is like fixed, then we hold the beam like this around 18 to 19 millimeters, which make sure we should not go over 20 millimeter. Then we leave it out. And that's how it shows on the graph until 1.2 seconds. They're on the high section. And after release, then you can see the graph decaying like this because they're absorbing everything. So it's coming back like this. So yeah, as you can see, after the beam was released, the graph represented a underdamped free vibration response. And after this, then we need to find the natural frequency, damping ratio, and damped natural frequency by using the logarithmic decrement method, And then we set up the two peaks around 35 cycles. Then after we apply everything in with those two equations, then the damping ratio was around 0.6%. And both natural frequency and damped are almost identical to 15.07. And after this, then we compare the experimental versus the theoretical responses. As you can see on the graph, both graphs represent the decay to each other. To figure out this, we apply the underdamped SDOF, the equation. Then after we apply the initial conditions, which is when x at the 0, then we turn it as the initial displacement, and then the velocity at the initial displacement must be 0, and then that equation turns to this. Then we apply this to the theoretical response. And after this, we need to find the spectrum and see if the time domain and the FFT analysis were aligned to each other. And after we applied the FFT, the peak was around 15 hertz, which we got 15.07, very close to each other. And then you can see on the graph the peak at the 15 hertz. That's also means the natural frequency of the system. And after we find they at a steady condition or no, excuse me, at a steady condition with the load, then they had a 15.07 hertz. Then we got to find like, does it work with the different conditions? So now after this, then we put the beam like this, and then we drop the coin like 25 cents and then drop it around like 4.4 around to 6 inches of the height. And you can see the displacement spikes occurs around 1.8 seconds. And after 1.8 seconds, the system presents the free vibration and then amplitude. You can see the decay over by the time, by the damping. And then for spectrum, we apply the FFT, just make sure everything's lined together. And then the peak was around 15.0667 hertz, and no additional peaks were absorbed. And also consistent with the time domain analysis. So the last one that we did, we applied the thin tape and thicker tape. So let's to see is there any difference with the damping ratio and how does it work with the decaying there. As you can see, these are the two setups. And then comparing everything, no treatment case, tape 1, tape 2 case, you can see when the tape was edited, which will increase the damping, the decaying ratio is getting faster and faster. So the treatment goes like this. Tape 1 is a little bit faster, and tape 2 is way much faster. And you can see the damping ratio difference table. No tape, the damping ratio was 0.06%. Tape 1 was 1.2%. Tape 2 was 1.47%. So all the summaries, all the natural frequency and that natural frequency are almost same with the different conditions, but the damping ratio are all different. As the tape was getting thicker, the damping ratio increased. And I will say the possible error for the case 4 is the human error that might occur while calculating number of cycles. So conclusion is the cantilever beam reacts with the linear system. Between voltage and displacement, a linear relationship exists, which also work with the Hooke's law. All 4 cases with different conditions presented similar or the same natural frequency. The last one is increasing damping reduce the amplitude more quickly. These are the references. Do you have any questions? Well, thanks so much.